In this video, I will show you how to take a parametric equation where x and y are written in terms of a third variable like t, and rewrite it as a rectangular equation with only x's and y's. This is called eliminating parameters. But first, we will do a brief exploration on our graphing calculator. Make sure your calculator is in parametric mode, so hit the mode button and go down to here where it says function versus parametric, and make sure that parametric is selected. Once you've done that, go back to y equals. I want you to change one more thing. Arrow over here to the left where this little line is and hit enter. And then I want you to go down to the line and use your left or right arrow keys to change this to this one. Alright, and I'll show you what that does in a minute if you don't already know. And we're just going to hit OK. Okay, so our exploration will be with this parametric equation. So go ahead and type this into your calculator for x and y. And 7 cosine 5t. Let's hit graph and see what happens. Wow, that was crazy. Hit the window button real quick. Sometimes the t step affects the smoothness of the curve. So let's change this to 0.05 and see if that has any effect on the graph. Hit graph again. Alright, that just makes the curve a little bit smoother. I like that. Let's play around with the coefficients of t and see how that changes the graph. So let's make this a 2, and let's make this a 4. See if that has any effect. Wow, that had a major effect on the graph. Okay, let's see. I'm going to put this back to a 3. All right, let's see what happens now. Wow, so it seems like very small changes to these coefficients makes a dramatic effect on the graph. What if these were both 1s? Okay, wow, this is kind of fun. So these graphs fall into a family of curves named lysogous curves. Here's another parametric equation. Let's type this into the calculator and take a look. So I've typed in my parametric equation, and under window I have the parameter t set to go from -10 to +10. Let's hit graph and take a look. Okay, so it seems to be a parabola. Sometimes it's hard to tell what the shape is going to be looking at the parametric equation, but we can use a process called eliminating the parameter to convert the parametric equation to a rectangular function or Cartesian function with which we are more familiar. The steps for eliminating the parameter are as follows. First, take one of the variable equations and solve for t. Then substitute that into the other variable equation and simplify. Notice that occasionally you will need to restrict the domain of the rectangular function to get the identical graph. Let's isolate the t from the first equation by adding 1 to both sides. That will give us x plus 1 is equal to t. Now let's substitute this expression into the other variable equation. So y equals t squared minus 2 becomes y equals x plus 1 squared minus 2. And that's it. This is a rectangular equation relating x and y. In fact, we can easily identify this as the equation of a parabola where the parent function y equals x squared has been shifted 1 unit to the left and 2 units down, which is exactly what we saw on the graphing calculator. Pause the screen and try to convert this parametric equation to a rectangular equation. So I'm going to assume that you've done that. Let's take the x equation and isolate the t. We'll start by adding 4 to both sides. So that's x plus 4 is equal to 2t. Next, we divide both sides of the equation by 2. So that's going to be 1/2 x plus 2 is equal to t. Now we take this expression for t and we substitute it into the other equation. So y equals t squared becomes 1/2 x plus 2 squared. Hey, we forgot to take a look at the parametric equation on the graphing calculator. Let's do that now. Here's the parametric equation typed in. Notice that we want the t to be greater than or equal to 0. So I will accomplish that under the window button by letting t min be 0. And I think a t max of 10 is probably good enough. If I wanted to be extreme, I'd make this like 100. So let's see. Alright, well, assuming that it doesn't come back and do the other half, it looks like we're getting half of a parabola, starting at starting at -4 and then going to the right. So this is going to be some type of a parabola, but we will have to restrict the domain to make it match the original. On the graph, we could see that the x values are always greater than or equal to -4. But how could we come up with this domain restriction without graphing on the graphing calculator first? Let's start with this restriction for t. T is greater than or equal to 0. We came up with this expression for t in terms of x. So if we know that t has to be greater than or equal to 0, that means that 1/2 x plus 2 must be greater than or equal to 0. Subtracting 2 from both sides, we have 1/2 x is greater than or equal to -2. And multiplying both sides by 2, we get x is greater than or equal to -4. So that's how you could get the domain restriction. Let's put example 3 into our calculator and take a look at it just for fun. A parametric equation in this form means that x equals 1 minus 2t and y equals 2 minus t. So I've typed that parametric equation into my calculator, and now I want to adjust the window for t. We are given the restriction on t from -5 to +2. So let's let t min be -5 and t max will be +2. Let's take a look. Interesting. This looks like a linear equation. It's a linear graph, but it has this restriction that x is greater than or equal to -3. Let's see if we can algebraically convert this parametric equation into a normal Cartesian equation, a normal rectangular equation. Let's isolate the t from the x equation. Subtracting 1 from both sides gives us x minus 1 equals -2t. Dividing both sides by -2 gives us -1/2 x plus 1/2 is equal to t. Now let's substitute this expression for t into the other equation right here. We get y equals 2 minus -1/2 x plus 1/2. So that's 2 plus 1/2 x minus 1/2. Let's see, 2 minus 1/2 is 3/2. By the way, 2 minus 1/2 is the same as 4/2 minus 1/2, which gives us 3/2. Or you could think 2 minus 1/2 is 1.5, and maybe you know that that is 3 over 2. Anyway, this is the linear equation. But how do we get the restriction that will correspond to the restricted value of t that we were given? Early on, we found this expression for t. So the bottom line is I'm going to take this and plug it in right there. So far, we have negative 5 is less than or equal to negative 1/2 x plus 1/2, which is less than or equal to 2. We need to get x by itself. First, I would like to get rid of these fractions. So let's multiply all sides of this inequality by 2. So that will give us negative 10 is less than or equal to negative x plus 1, which is less than or equal to 4. Next, let's subtract 1 from all sides of this inequality. So that will give us negative 11 is less than or equal to negative x, which is less than or equal to 3. Finally, I just want x, not negative x. So let's divide all sides of this inequality by negative 1. Dividing an inequality by a negative number reverses the direction of the inequality. So this will give us 11 is greater than or equal to x, which is greater than or equal to negative 3. Or written more naturally, negative 3 is less than or equal to x, which is less than or equal to 11. Which means that x is between negative 3 and 11. So kabam! There you go. Let's look back at the graph. At first I thought that the domain would just be greater than or equal to negative 3, but I think that's just because the graph was going off the screen. To verify that hypothesis, let's change the x max to something bigger, like 15, and take another look. So now we see that our linear graph is restricted to values of x between negative 3 and positive 11. Ooh, let's do a trig example. Let's isolate the t in the x equation, starting by dividing both sides by 2. So that will give us 1/2 x is equal to cosine t. We can isolate the t by doing the arc cosine of both sides of this equation. So we get arc cosine of 1/2 x is equal to t. Wait, before we go any further, let's type the parametric equation into our calculator and see what it looks like. So adjusting the window for the restriction on t between 0 and 2 pi, so t min will be 0 and t max will be 2 pi. Okay, it looks like an ellipse. Or actually, it could be a circle. It's probably a circle. It just looks like an ellipse because the screen is a rectangle. It's a little squished. Now, back to our calculations. We had just found an expression for t. However, arc cosine is tremendously difficult for us to work with. So let's not do this. We can avoid the arc cosine by stopping here at x over 2 equals cosine t. Similarly, if we take the y equation and divide both sides by 2, we get y over 2 is equal to sine t. But what now? Well, this is why we learned those Pythagorean identities earlier in the year. And the most important one was sine squared theta plus cosine squared theta is equal to 1. So, written in terms of t, that becomes sine squared t plus cosine squared t is equal to 1. Remember that sine squared t just means sine of t squared. And similarly, cosine squared t means we've got the cosine of t squared. So I'm going to take this and substitute in our two expressions for cosine t and sine t. So we get y over 2 squared plus x over 2 squared is equal to 1. Getting rid of the parentheses, we have y squared over 4 plus x squared over 4 is equal to 1. If we multiply both sides by 4, we get y squared plus x squared is equal to 4. Or written in standard form, that's x squared plus y squared is equal to 4, which is the equation of a circle with radius 2, which is exactly what we saw on the graphing calculator. Notice that in this case we do not need to restrict the domain in order to match the restriction on the t value. Here's another trig example. We have x equals 4 secant t, and we have y equals 4 tangent t. Looking at the blue equation, we have x divided by 4 is equal to secant t. From the red equation, we get y over 4 is equal to tangent t. Here's a set of variations on the main Pythagorean identity, sine squared theta plus cosine squared theta is equal to 1. If we were to divide every term by sine squared theta, we would get 1 plus tangent squared theta equals secant squared theta, for example. I'm mentioning that because in the problem we're working on now, I see tangent and secant being mentioned. Let's use this identity to build our rectangular equation. So we have 1 plus tangent squared. This is our expression for tangent right here. So this becomes 1 plus y over 4 squared is equal to secant squared. Well, this is our expression for secant. So this will equal x over 4 squared. So this is 1 plus tangent squared equals secant squared. Getting rid of these parentheses, we have 1 plus y squared over 16 is equal to x squared over 16. If we subtract y squared over 16 from both sides, we get 1 equals x squared over 16 minus y squared over 16. I'm sure you won't mind if I flip this equation around. This is the equation of a hyperbola. So one nice thing about parametric equations is that they're easy to type in to the calculator. It would actually be pretty difficult to type this equation into the calculator because we would have to get y by itself, and there would be square roots and plus or minus and all of this stuff. But we can type this parametric equation in pretty easily. Let's do that now. This is my 4 secant t and my 4 tangent t. There is no secant button, so I had to do 1 over cosine. And no, that is not the same as this inverse cosine. This is like arc cosine, which is completely different. So this is how you would have to type it in. Under the window, I'm going to let my t-min go from -10 and my t-max go to +10 with a t-step of 0.05. Let's see what we get. Okay, so there's some repetition happening in there, but you can see the hyperbola and these blue lines are the asymptotes. For example 6, we have x equals 1 over radical t and y equals 1 over t. Let's type in these parametric equations right from the start and see what we're looking at. Okay, I've typed in the parametric equations. Let's take a look at the graph. It is graphing very slowly. This looks like half of a parabola, so we will probably have some domain restrictions. Let's start by isolating the t from the x equation. When you have something that's equal to a fraction, you are allowed to swap the thing that's out here by itself with the denominator. So I'm going to immediately get the square root of t is equal to 1 over x. It's a little shortcut. To get rid of the radical, we are going to square both sides. So that will give us t is equal to 1 over x squared. Next, we will substitute this in right there. So we get y equals 1 over x squared. When you put 1 over a fraction, it means take the reciprocal of that fraction. Or you could just think to yourself, whenever you divide by a fraction, you simplify by multiplying by the reciprocal. Either way, we're going to end up with y equals x squared. But that is a whole parabola. That's the parent function for a parabola. So where do the restrictions come in? Notice that t is under a radical and in the denominator. This tells us that t has to be greater than 0. T cannot equal 0 because then we would be dividing by 0, and that's not allowed. And we can't take the square root of a negative number, so t has to be greater than 0. Remember that t is 1 over x squared, so this becomes 1 over x squared must be greater than 0. Well, this is almost always true. If you take any number and square it, it's going to give you a positive number. Except for one, and that is that x cannot equal 0. But other than that, this will always be true. X does not equal 0 is not enough of a restriction. Remember, we are looking at only the right-hand side. So why are we only getting the right-hand side and not a whole parabola maybe with a hole in it right at 0? To solve the mystery, we need to go back to here. X is 1 over the square root of t. T cannot be 0 because then we'd be dividing by 0. And also t cannot be negative. You can't take the square root of a negative number. So just imagine that t is always a positive number. That means this expression is always going to be greater than 0. In other words, x is always going to be greater than 0. With this domain restriction, y equals x squared is now equivalent to the original parametric equation. Let's do one more example, and let's make it a trig example. This is another way of expressing the parametric equation x equals 3 plus sine t, y equals 2 cosine t. Normally we try to get t by itself, but the only way to do that would be to get arc sine and arc cosine, and we don't want to do that. So let's get sine t by itself, and let's get cosine t by itself. Subtracting 3 from both sides, we have x minus 3 is equal to sine t. Dividing both sides by 2, we have y over 2 is equal to cosine t. Never forget your Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Since sine t equals x minus 3, sine squared will be x minus 3 squared. Plus cosine squared, so that's plus y over 2 squared. And then equals 1. If we write this in standard form, we get x minus 3 squared over 1 plus y squared over 4 is equal to 1, which is the equation of an ellipse. Let's type the parametric equation into the calculator and see if we do get an ellipse. So this looks very circular, but I think it's only because the screen is a rectangle. Notice that the units on the x-axis are spread out more than they are on the y-axis. We can adjust that by hitting Zoom Square. So let's go Zoom and then Option 5. There's your ellipse.